Maybe this has happened to you. Is it the same as lightning? What do you notice here? And here, what is pulling the bulb? Rubbing the shoes against the wool rug caused a spark we could see. Rubbing the comb against hair made a pull, an attraction, and made sparks we could hear. This is a kind of electricity. We can try rubbing many things together to see this happen. Where does the electricity come from? The plastic cup? The water? Is it in the balloon? The shirt? Is it in the wall? Experiments like these have helped scientists learn that electricity is a part of everything. Sometimes some of the electricity in one thing can be rubbed off onto something else. Then we say that thing is charged with electricity. It has extra electricity. That charge can attract or jump to something else as a spark or lightning. We can build a machine to rub two things together continuously. See what happens then. Does this remind you of lightning? What causes lightning in the sky? Perhaps now you can find out. Electricity we get by rubbing is interesting, but it isn't very useful. To make light for us, or heat, or to turn motors, we need electricity that can be controlled. Electricity that will flow when we want it to. How can we make it flow? We know we can get a current of electricity by using dry cells. With this meter, we can measure that current. But now watch. Here is a penny made of copper and a dime made of silver, two different metals. Of course, there is no current flowing in the wires, and none in the coins either. Electricity, just like that from the flashlight cell, though much, much weaker. Instead of salt water, suppose we try something else, a lemon. The two different metals can produce an electric current in lemon juice, too. This time the current is flowing the other way. How about two coins or metals that are the same? When the metals are the same, there is no flow of electricity. How about a nickel and a quarter? They are different metals. And let's try something else instead of the lemon. There is a chemical action here that is causing the electricity to flow. Is this the way the cells of batteries work? In a flashlight cell we've cut open, we can see the parts that are similar to the cells we have just made. This center pole and the whole case enclosing the cell are like the different metals. the penny and the dime or the quarter and the nickel. And this damp paste between them is like the salt water, the lemon juice, or the damp apple. Do you think this cell can still produce an electric current, even split open like this? Let's see. Can you tell why a current can still flow from this cell? Why breaking it open didn't ruin it? The electric cells we made didn't produce enough current to light a lamp, so we used a meter. But if we didn't have a meter, there is another way we could find out whether a current of electricity is flowing. This compass points north because it is attracted to the north pole of the Earth. Watch the needle of the compass when a magnet is brought near. The north pole of the magnet attracts one end of the compass needle, but the south pole repels that end and attracts the other. See if this wire has any effect on the compass. Now see what happens when we connect the ends of the wire to a dry cell and a current flows through it. And see what happens when we switch the direction of the current. When the wire carries a current, does it act like a magnet? You can make a simple meter by winding a coil of wire around a compass. Let's see if it works. And if we reverse the current, we have been able to make something to show when electricity is flowing because the current made the wire act like a magnet. If we coiled wire around an iron bar, could we make that act like a magnet too? Let's try it. We could do this with a nail or anything else made of iron or steel. Doesn't work this way. Let's see what will happen when we put an electric current through it. The current isn't flowing yet. When we connect the other end of the wire, the current can flow. What will happen when we stop the current? We have made a new kind of magnet. One boy once called this a sometimes magnet because it only works some of the time when we want it to. Or we might call it an electricity magnet, or to make it shorter, an electromagnet. Do you think electromagnets are very important? Think of all the things that run on electric motors. Without electromagnets, these things would not be possible. All electric motors, from the largest to the smallest, work in very much the same way. Let's see how. Do you remember what happens when two magnets are close? The poles that are different pull toward each other. But when the poles are the same, see what happens? By changing the poles, we can make this magnet turn around and around. The poles of an electromagnet change every time the current is turned around. First north, pushing away the other north, pulling the south. Now switch, and it's south, pushing away the south, pulling the north. How could the direction of the current be changed without using hands? Here is a coil of wire around an iron bar. Now look at this part. See how it's split in two? This is a commutator. One end of the wire coil is connected to one side of it, the other end to the other side. When a dry cell is connected to this post, the current will run down and across this metal strip, down this side of the commutator, and into one end of the wire. It will flow through the coil and come out the other side. But if we turn the coil, this metal strip or brush will touch the other side of the commutator, and the current will go into the other end of the coil where before it came out. Every time this happens, the current will go in the opposite direction in the coil. What will that do to the electromagnet? This compass shows us that the pole of the electromagnet near it is north. Now let's move the coil just enough so that the current will go in the other side. There. Now the pole has switched to south. Now north. Now south. If the south pole of another magnet were near, what would happen? Here we have placed the north pole of a magnet on one side of the coil and the south pole on the other. Let's pass a current through the coil and see how push and pull can make a magnet spin. This spinning electromagnet is called an armature. Electricity flowing into a motor made the armature spin. Now let's see if spinning the armature will make electricity flow out of the motor. Do you see what is happening? Would you like to know why? Here is a magnet and a coil of wire attached to a meter that shows when electricity is flowing. Suppose we put the magnet near the wire. The needle shows there is no current flowing. But did you notice something there for a moment? Let's try again. Watch the needle. There. And there again. Can you see what is happening? The meter doesn't show any current when the magnet isn't moving. But there is a flow of current when the magnet moves, and a flow in the other direction when the magnet moves in the other direction. Does it matter if the coil is moved instead of the magnet? A coil of wire, a magnet, and a way to turn one of them, and you have a machine to produce electricity, a generator. If you built this generator large enough, you could light an entire city. But of course you'd have to find some other way to keep it turning. What are some other ways? Water power is one thing you might use. At many waterfalls and dams, huge generators have been built. They're far bigger than our hand generator, but they make electricity in the same way, with coils of wire, magnets, and turning. Wires carry the electric current great distances to our homes. Electricity that can work for us. That can be changed into light. That can be changed into heat. That can be changed into sound. That can be changed into motion to run so many different things. Even the machine showing this movie that can change electricity into motion, into sound, and into light.